All right. So let me just recall where we stopped last time. So last time, we basically went through some properties about the geometry of symmetric spaces of PSLDR. And then we ended up with this definition, right? So let me just remind you what it is again, okay? So we start with a Fuchsian group. So I want to emphasize here that Fuchsian means discrete infinite. I'm not assuming geometrically finite here. Okay? Any infinite discrete subgroup of PSL2R, Fuchsian group, and I choose a number k from 1 to d minus 1. And then I say a representation rho from gamma to PSLDR is k transverse if there exists a map, which I call C, from the limit set of gamma into this partial flag manifold, right? So this partial flag, so it's a k-dimensional subspace inside of a d minus k-dimensional subspace of Rd, okay? The space of partial flags that is transverse, okay? So that means that any distinct pair of points in lambda gamma gets sent to transverse pairs of flags. Rho equivariant, okay, that means that the gamma action here and the rho gamma action here commute, is intertwined by C. And then the last property is called strongly dynamics preserving, right, which I write as SDP here. And let me remind you what it says. It says that if you have a sequence of elements in the group, okay, so that the sequence, when you apply to some fixed base point in H2, goes to some point X in the limit set. And when you take gamma I inverse, the sequence of inverses, you apply to the base point, it goes to Y, okay? Then, when you take this sequence and you feed it to the representation, you look at it, how it acts on the flag manifold, you would take every flag F that is transverse to Y to C of X, okay? So that's what this strongly dynamics preserving property. Okay, and we saw that, I told you that once you, okay, we don't have any examples yet, but if you have a representation that is K transverse, it gives you a few things. Firstly, it tells you that all the singular, if you take a diverging sequence in a group, the singular values of rho of the sequence has to go to infinity. Okay, and we saw that this kind of representation has to be type preserving, meaning that a hyperbolic element in gamma gets sent to an element in PSLDR where there's a k and there's a gap between the k and k plus 1 singular value. And also, if you take a parabolic element in gamma, it gets sent to an element that is what we call weakly unipotent. Okay, so that means that if you take the Jordan decomposition of that group element, okay, the unipotent part has to be not the identity, and the semi-simple part has to be elliptic. Okay, so your eigenvalues are all absolute value 1. Okay, yeah. No, the k does not enter into that. Yeah. So no, the k also does. So the hyperbolic. So okay, let me write that out. Okay, so what does type preserving mean? Okay, so type preserving means that, okay, I think I might have said something wrong, but that's okay. Let me write it down. So it means that if gamma in gamma is hyperbolic, meaning that the two eigenvalues have distinct absolute values, this means that rho gamma alpha of lambda of rho gamma alpha k of lambda of rho gamma has to be positive. So lambda of rho gamma is the Jordan projection, right? So these are the absolute value of the eigenvalues of rho gamma. And so there's this telling you that the kth eigenvalue of rho gamma is strictly larger than the k plus 1 eigenvalue of rho gamma in terms of absolute values. Okay, and then if gamma in gamma is parabolic, okay, this means that when you take the Jordan decomposition of rho gamma, so that is you can decompose it into a semi-simple part and a unipotent part where these two commute. Okay, then so maybe if is the Jordan decomposition. Okay, then rho gamma, the semi-simple part, is elliptic. Okay, that means conjugate into a maximal compact. And the unipotent part is not the identity. Okay, so that's what I mean by type preserving. So it's like essentially unipotent, except that you might have to multiply by some compacting that there's rotation on the eigenvalues. Okay. Okay, so that's basically where we stopped last time. Oh, another thing I should mention is that the strongly dynamics preserving property, if you row equivariant transverse strongly dynamics preserving maps are unique. Right? So this map C is unique to rho if rho is K transverse. Again, we call this map C the K limit map of rho. Okay, so that's where we stop. So let me give you one example of a K transverse group in higher rank situation. Okay, so what you do is you take PSL2R and you embed it irreducibly into PSLDR, right? So last time, I spent quite a bit of time constructing what this iota is for you, okay? You embed it irreducibly. And then if you take this iota and you restrict it to any function group, okay? So this iota, okay? So you take iota and you restrict it to any function group, okay? Discrete infinite group, this group from gamma to PSLDR, this is K transverse for all K. Okay, so maybe example. All right. So again, I don't need gamma to be finitely generated here. Okay, we can use the kind of groups that show up in Ara's talk. This would be fine. Okay. Okay. Now I'm going to move on to talk about positivity. This is one of the things that I promised you to do. Okay. All right. So I'm going to let you be the set of upper triangular, unipotent upper triangular matrices in SLDR. Okay, and then I'm going to let U larger than 0 be the set of elements in U, set of matrices in U, okay, where every minor that is not forced to be 0 is positive. Okay, so let me give you an example to illustrate what I mean here. So let's look at the SL2R case. Okay, first I take an element in U, right? So an element in U is upper triangular unipotent. So it looks something like this. Okay, and so what does it mean for this guy to be in U greater than 0? Okay, I want every minor that's not forced to be 0 to be positive, okay? No, the minor is a number, it's a determinant of a submatrix. That's what a minor is, okay? So let's check all the minors here. Okay, so that's first we look at the 1 by 1 minors. There are 4 of them. Okay, this guy is forced to be 0 because I'm upper triangle. Nothing I can do about that. For you to be in U greater than 0, the other 3 minors all must be positive. Okay, so these are both 1s which are positive. So the condition here is that A is bigger than 0. And then the 2 by 2 minors is 1, so that's also positive. Okay, so this guy here is in U greater than 0 if and only if A is positive. Okay? Now let's look at SL3. Okay, so I do the same thing, right? I take a upper triangular unipotent matrix. Okay? And what does it mean for this guy to be in U greater than 0? Okay, so let's go through, right? So again, we look at the 1 by 1 minors. Okay, so these 3 are forced to be 0 because I'm upper triangular. And then I have A, B, and C. So these 3 numbers must be positive. Okay, then now we move on to the 2 by 2 minors. Okay, so let's check all of them. So, okay, look at this submatrix, right? 0, 1, 0, 0. This is forced to be 0. The minor, right? The determinant of this matrix is forced to be 0 because I'm upper triangular. Okay, so there's nothing I can do about that. 1A, 0, 0, also forced to be 0 by being upper triangular. Okay, and then here, but here you have A, B, 0, 1. That is not forced to be 0, but that minor is just A. Okay, but that I've already written A has to be positive. And then 1C, 0, 1, that determinant is 1. Now I have A, B, 1C. So this determinant is AC minus B. This has to be positive. Okay? And then if you go on and check all the other 2 by 2 minors and the 3 by 3 minors, you see that these are the only conditions. Okay, so to be in U greater than 0, it means that these conditions must be satisfied. Okay, and you can see that as your matrix gets bigger and bigger, you get more and more conditions to check. Okay? Okay, but an important fact about this U greater than 0 is that it's actually a semi-group. Okay, so fact. Okay, if U1 and U2 are in U greater than 0, okay, then the minus of U1, U2, the product, is at least the minus of U1. Okay, so what do I mean by this, right? So every time I take a minor of U1, U2, I'm choosing a submatrix, right? So there's a corresponding minor of U1. I'm saying that you have this inequality, okay? And this basically comes from the formula that, I forget the name of that formula, but you can write down the minus of the product as a sum of products of the minus of U and U2. So from that, you can see this, okay? And so from this, this tells you that this U greater than 0 is a semi-group. Right? When you multiply, because if the minus of U1 are all, the non-zero minus of U1 are all positive, then the same has to be true for U1, U2, okay? All right, so that's my U. Now I'm going to look at, okay, so then we're going to look at the flag manifold. Okay, so let FRD denote the set of complete flags. Okay, so what is this? So a complete flag, I'm usually going to denote it by F. It's a nested sequence of subspaces, one of each dimension. So I'm going to denote by F1 to Fd minus 1. Okay, so that where each Fi lies in the Grassmannian of I planes in Rd, and Fi lies in Fi plus 1 or I. Okay, so this is the space of complete flags. So this turns out to be a compact, I mean, there's a natural manifold structure here, and this is a compact manifold, which is SLDR, PSLDR homogeneous, okay? Okay, then I'm gonna, inside of this flag manifold, I'm gonna have two special flags, which I'm gonna denote by F plus and F minus, okay? So F plus is the flag such that this I-dimensional piece is the span of the first I standard basis vectors of Rd. Okay, and F minus, right, is the flag whose I-dimensional piece is the span of the last I standard basis vectors of Rd. Okay, some standard pair of flags. Okay, so then here's the definition. Okay, so I'm going to let K be any integer that's at least 3. Okay. Then a K-tuple of flags F1 to Fk in FRD right is positive okay if there exists elements U1 to UD minus UK minus 2 in U greater than 0, right? And some G in PGLDR. Okay, not PSL, but PGL, okay? Such that when you apply G to this tuple of flags, so you can normalize it so that it looks like F plus, then the product of U1 to UK minus 2, F minus, the product of U1 to UK minus 3, F minus, and keep going until U1, F minus, F minus. Okay, so that's what the definition is. Okay, so let me so what is it saying, right? So if you have a tuple of flags, let's say I pick the F plus and F minus as my standard ones, right? This means that the remaining tuple has to be of a certain form that coming from elements of this semigroup. You take products. Okay, so notice that all of these elements, they are products of these elements, so they all live in U greater than 0 as well, because this is a semigroup. Okay, and if you allow yourself to move things by something in PGLDR, that's still positive. Okay, so if this is the first time you're seeing this definition, it looks like, where does this come from? Okay, so I hope that I can justify this by showing you some low-dimensional examples. Okay, so let's look at the example of SL2R. Okay, so in SL2R, what does it mean? Okay, so in SL2R, right, what is my F plus and my F minus? My F plus is E1, right? So that's the point 0. Okay, that's the point 1, 0. This is F plus. No, 0, sorry, F minus. This is 1, 0, 1. Okay, and then F plus is 1, 0, right? Okay, and so what does it mean? Okay, then what does U1 F minus look like? So this U1 is a matrix of this form, right? 1A, 0, 1, where A is some positive number. So when I apply that to F minus, that moves it to A1, okay? So this is A1. Okay, maybe A11. So my U1, let's say I write it as 1A101. Okay, that's A11. Okay, so this is my U1 times F minus. Everyone follow so far? Okay, then now I get U1, U2, the next element is U1, U2 times F minus. Right, but what is U1, U2? So if U1 is 1A101 and U2 is 1A201, the product of those two is 1, A1 plus A2, 0, 1. So the next point is further up here. There's U1, U2 times F minus, and you keep going, okay, and you get here. Okay, so in the case of SL2R, this is just saying, what does it mean for a tuple to be positive? It just means that a tuple is cyclically oriented. Okay, it can be counterclockwise or it can be clockwise. Because this G, I can take it in PGL2R, I can reverse orientation. So it can be counterclockwise or clockwise. But as long as it's cyclically oriented, that's what it means for this to be positive in the SL2R case. Any questions? Okay, so in particular, if you take any 3 distinct points in RP1, that triple is positive. Doesn't matter how I order it, right? It doesn't matter, yeah, because you have A, B, C, right? I only care about the cyclic ordering, and these 3 points are always cyclically ordered. Okay, so any triple is positive. Okay, so that's the SL2R case. Now let's look at the one dimension higher. Let's look at the SL3 or PSL3. Maybe I should just put P, since I've been using P the whole time. Okay, so now I'm not going to give you all the details. I'm just going to tell you what the answer is. Okay, what does it mean for a triple to be positive in this case? Okay, so I'm going to draw a picture, right? So now this is going to be a picture in RP2. Okay, so how do I draw flags? Flags in R3 in RP2, right? So what's a flag in R3? It's a line that lies in the plane, right? So when you projectivize, what does a flag look like? A flag is a point, right? This is what the line is. When you projectivize, you get a point. The line is inside of a line. This is the projectivization of a plane. Okay, you can think of this board as some affine chart of RP2. I'm drawing all my flags in the affine chart. Okay, so it turns out, okay, you have to compute stuff, but it turns out that requiring you to have a positive triple of flags is saying that you want to have a tuple of a k tuple of flags that osculate a convex domain, a properly convex domain. Okay, so I have a bunch of flags here. Okay, it's positive means that you can find some properly convex domain or some convex domain in this affine chart. Okay, whose boundary passes through all the points and all the lines are tangent to it. Okay, that's what positivity means in SL3R. Okay, my convex domain. Any questions about that? Okay, so in general, there are some properties that positive tuples of flags have. So in general, Okay, positivity is it's not clear from the definition, but this is really a property of the cyclically ordered tuple of flags. Okay, so F1, so okay, first property that F1 to Fk is positive if and only if I cyclically permute it. So F2 to Fk, F1 is positive. Okay, and this is equivalent to when I reflect. Okay, and I just reverse the order of this tuple. Okay, so being positive is invariant under dihedral permutation of the flags. Okay, you can see that is true in this case, also true in this case. Okay, yeah. Right. So okay, if you have k, so if you have fixed k, then only k points, right? But if you keep increasing, then you're going to get more and more points. So in this case, let's say this is your f plus, right? And maybe this is your f minus. Okay? When you increase, you're going to get more and more flags that are tangent to this thing. And yeah. Okay? Any other questions? Yeah, so the way that this is designed, the design is, notice that if I just drop the last flag, right? And then I multiply throughout by U1 inverse. F plus doesn't change. And now this is just the product of U2 to UK minus 2, now U2 to UK minus 3, and so on. And then this last one just becomes F minus. So when you drop the last flag, it's still positive. Okay? But really, okay, any other questions? Okay, so first property, let me see what's my next property. Oh yeah, so second property is that positivity is preserved by taking a subsequence of your k tuple. Okay, so F1 to Fk is positive, right? Implies that Fi1, Fik is positive. Okay, for any 1 less than equals to I1, less than I2, less than Ik, less than equals to, In, less than equals to K. Okay, so if you just remove a few flags from your tuple and you look at what's left, that's still positive. Again, clear from in these two examples. Okay? And then the third one is saying that if you have a tuple F1 to Fn minus 1, Fn is positive, so you have a positive tuple like this. Okay, and you have another positive tuple, right? F1, Fn minus 1, Fn to Fk is positive. Okay, then F1 to Fk is positive. Okay, so let me draw a picture. Okay, maybe let me, in the SL, let's look at what this is saying in the SL2R case. Right? The SL2R case is saying that, suppose I have a flag F1. Okay, and then I have a tuple that's a bunch, like F1, I go all the way to Fn minus 1 and Fn. Okay, and you have a bunch of other flags along the way. Okay, that's my first tuple. My second tuple starts with F1, Fn minus 1, Fn, and I have a bunch of other flags along the way to Fk. Okay? So what this is saying is that if you have an original tuple of F1 to Fn that's positive, and you have another tuple that's F1, Fn minus 1, Fn, and so on to Fk that's positive, when you put them together, it's still positive. Okay? You can check that that's also true in this situation. Right? So, but this property is true in general. Okay, and maybe my point is that in most of the arguments I'm going to be making later, I don't actually use the original definition of positivity. What I really use are these properties of positivity. Okay? And so if you find a more general class or a more general property where the same more general property, okay, I'm thinking of theta positivity here, where the same properties hold, all my arguments go through. I don't actually use this definition. I just use the consequences of the definition. Okay? Yeah. No, K is bigger than N in this case. K is, sorry, yeah, maybe, so that the picture here, maybe, okay, is you have F1 to Fn, and then Fn minus 1 Fn, then Fn plus 1, Fn plus 2, all the way to Fk. Yeah, that's what I mean there. Maybe I should have, I'll put in more. Right, K is bigger than N in this case, okay? Okay, so now we can move on to the definition of a positive map. Yes? No, so that will not be true, yeah. Okay. Okay. Okay, so here's a definition of a positive map. Okay, let S be a subset of the circle. Okay, I know people have been using S as a surface, but my S here is just a subset of a circle. Okay, and then okay, I need to know that the size of S is at least 3. Okay, then a map C from S to FRD is positive, okay, if C of x1 to C of xk is positive for all x1 to xk cyclically ordered in S. Okay, so S is a subset of a circle. There's a cyclic order on S, right? So what this is saying is, I say a map is positive if it preserves the cyclic order in the positivity sense. So when it takes a positive tuple in S, meaning a cyclic order tuple in S, to a positive tuple of flags. Okay? So for example, if you take a circle and you send it, let's say you have a properly convex domain with C1 boundary, something like this, right? And you have a map from the circle to the boundary of this domain, and you put in the tangent lines as well. That's an example of a positive map. Right? You take every cyclic order tuple to a cyclic order to a positive tuple of flags. Does it make sense? Okay. Okay, so first observation. Okay, if C from S to FRD is positive, okay, then it is transverse. Okay, meaning that it will take any distinct pair of points to a transverse pair of flags. Okay, and the reason is because you take F plus and F minus are transverse, right? And from the fact that you can cyclically reorder stuff and you can remove flags, you can from there it's not so hard to see that this map has to be transverse as well. Okay, because given any 2 points, you can basically make those 2 points F plus and F minus up to the G action. Yeah. Not yet. Not yet. Okay. There will be a group later, I promise. Okay, so proposition. Okay, so this one is less Okay, maybe this is the only proposition in my entire talk where I use the definition of positivity. Okay, the proposition says that if C from S to FRD is positive, okay, then the Hausdorff dimension of its image is at most 1. Okay? So why is this true? Anyway, this is foreshadowing because I'm going to be talking about Hausdorff dimensions of limit sets later. Okay, so some foreshadowing. But why is this true? So basically, what you view S as a subset of a circle and you parameterize S. Okay, and then so every point in S, you think of it as parameterized by some variable t. Okay, and then now you write down, you choose your F plus and F minus, and you write down to each point in your map, you write down what is U1 in terms of t, what is U1, U2 in terms of t, and so on. Okay? And what you see is that when you multiply these things, because of this property, right? Maybe let me say the map from S. So if you have C, right? You take every point here, I mean, you can think of it as t, and this gets sent to some ut times F minus. Okay, so okay, this is not well defined, but imagine I have my S. Okay, I don't care about, maybe I choose 2 points, X and Y, and I send that to F plus and F minus, I normalize that. Then the rest of the flex in between S and Y, I can write it as some ut times F minus, right? And this guy here, as you increase t, if you look at the minus of this ut, these are all monotonic functions. Okay, because of basically the way that it's defined, multiplying these matrices, the minus are getting bigger and bigger. Now, there's this well-known fact that if you have a function from a subset of R to R that is monotonic, then its graph has Hausdorff dimension at most 1. You use that same argument, you can prove this proposition. Okay, the monotonicity gives you that the Hausdorff dimension is at most 1. Okay? So proposition, okay? Okay, so far there's no groups, but now I'm going to bring in the groups. Okay, so maybe I should state this theorem of Fock and Gontroff that I mentioned last time, but I didn't state. Okay, so let gamma inside of PSL2R be a torsion-free uniform lattice, so a surface group. Okay, then rho from gamma to PSL-dr is a Hitchin representation. So we defined this last time, right? These were things that you can continuously deform from a discrete Heyfeld representation from gamma to PSL2R, and then you post-compose with this iota, this irreducible representation, and then you deform from there. Anything you can get that way is called a Hitchin representation. So a representation is Hitchin if and only if there exists a rho equivariant. Okay, continuous positive map. See? From the limit set, which in this case is the entire visual boundary of H2 to FRD. So this is a characterization, right, of those representations you can get from deforming the Fuchsian ones. Okay? And so, the way that I'm going to do things, I'm going to use this as my definition of what is a Hitchin representation for an arbitrary Fuchsian group. Okay? So like gamma inside of PSL2R be Fuchsian. So again, no geometric finite assumption here, right? Okay, a representation rho from gamma to PSL-dr is Hitchin. I call this Hitchin if there exists a row equivariant, okay, continuous positive map. C from the limit set of gamma to FRD. Yeah. Of a function. So you take a, in this case, okay, you take a convex, you take a torsion-free uniform lattice in PSL2R, and then, okay, and then you, okay, so, okay, maybe let me say it this way. You take, right, you take a torsion-free uniform lattice in PSL2R, and you take a representation of that lattice into PSL2R. So that's like any discrete faithful representation. Then you take your PSL2R and you put it inside of PSLDR using this irreducible representation iota. So when you compose that, you get a representation from your uniform lattice into PSLDR, and you allow yourself to continuously deform from there. Any such thing you get is called a Hitchin representation, right? And what they prove is that an equivalent way to say that is this existence of a row equivalent continuous positive map. Right. Right. So right. So I'm okay. So maybe I don't know what I'm extending the definition. Okay. So when gamma is a torsion-free uniform lattice, this agrees by the Ford-Gontroff theorem. This agrees with what used to be the Hitchin representations. Okay, but I'm extending it to a much more general class of gammas. Okay. And of course, the end goal is to prove that this class of Hitchin representations, in the case when gamma is geometrically finite, have all the correct properties, okay? They form entire connected components of the relative character variety, blah, blah, things like that, okay? Okay, but the next, okay, so I have this definition. The first thing I want to maybe give you an idea of the next result I want to get towards is to show that with this definition, okay, maybe I guess we saw examples of Hitchin representations, right? When gamma is convex co-compact. But when gamma is any function group, we also actually already saw an example of Hitchin representation, right? Namely, the one that I gave you as an example of a transverse representation. You take a discrete faithful discrete infinite subgroup, a function subgroup of PSL2R. You take an irreducible representation of PSL2R into PSLDR, and you restrict it to gamma. That is an example of a Hitchin representation. Okay. Okay, right. So the next thing I want to show is that these Hitchin representations are actually transverse for every k. Okay? Because if I can do that, then I immediately know a bunch of properties about these Hitchin representations. I know they're all type preserving. I know singular values have to go to infinity. Okay, and this is without geometric finiteness, right? Any function group will do. Okay? Okay, so let's see why. Okay, so the reason why you can do that. So let me write this as a proposition. Okay, so if F1, F2, F3 is positive, okay, then O of F1, F2, F3, I write it like this, okay, which I define to be the set of flags F such that in FRD, okay, such that F1, F2, F3 is positive, okay, is open in FRD. Okay, so in PSL2R, what is this saying, right? So in PSL2R, I have RP1, I have three flags, right? F1, F2, and F3. Okay? Then these all F1, F2 sub F3 are the set of flags F, so that F1, F, F2, F3 are positive. So in the PSL2R case, I'm looking at this collection of points. Okay, these are the collection of flags. This interval here is the collection of flags where F1, F, F2, F3 is positive, right? And this is an open set in RP1. So the claim is that in general, this gives you an open set in FRD. Okay? Now this is very important because this is telling you that every time whenever you have a positive curve, right? If you give me 2 points, or really 3, but the F3 is not that important, right? F3 you can move it around freely. It's really choosing. Basically, if you have 2 flags F1 and F2, there are 2 natural intervals between them, right? And what F3 does is it picks out one of them. Okay, so the F3 here is not as important. You can, if you perturb it a little bit, okay, the set doesn't change. But F1 and F2, if you perturb it a little bit, the set changes, okay? So this openness is telling you that whenever you have 2 points along this positive map, it actually determines for you an open set in the flag manifold. And what this open set is controlled by what F1 and F2 are. If you move F1 and F2 closer and closer to each other, this open set contracts to a point. You move F1 and F3 further from each other, this set gets bigger. Okay, like it behaves just like intervals. Okay? So as a consequence of this, right, the fact that you can control open sets in your flag manifold by just points along the limit curve, okay, allows you to prove that you have K transverse. Okay, so let me write this as a corollary. Okay, corollary: if rho from gamma to PSL dr, okay, is Hitchin. Okay, so gamma here is any function group. Okay, then rho is K transverse. Okay. Okay, so let me give you a sketch of the proof, right? Okay, so so to show that it's transverse, once you are positive representation, you already have this transverse row equivalent map, right? That's C, that exists on this positive map. So really what you want to show is this strongly dynamic preserving property. Okay, so what you do is you take any sequence gamma I, okay, such that gamma I takes your base point B0 to X, and gamma I inverse takes your base point B0 to Y. Okay, and then I'm going to cheat a bit. I'm going to assume that X and Y are distinct. Okay, so in general that's not true, but you have some tricks that you can reduce to that case. Okay, I'm going to skip that part. So suppose X is not equals to Y. Okay, then what's the picture that you have now? Okay, I'm not going to make it in terms of time. Okay, but that's okay. So the picture you have now is you have this disk, your base point B0, you apply your gamma i's, it's going to converge to X, and you apply your gamma I inverses, it's going to converge to Y. Okay? And then, when you are in this situation, the gamma I, right, you can assume that for I large enough, these gamma i's are going to be hyperbolic. In fact, the repeller of gamma I is going to converge to Y, and the attractor of gamma I is going to converge to X. Okay, in this situation. Okay, then I'm going to pick any 2 points A, B in the limit set of gamma. Okay, such that Y is less than A, less than B, less than X. Okay, so I guess I'm assuming here that I'm also cheating. I'm assuming that the limit set is the gamma is non-elementary. So you can do this. Okay, so you have a point A here, and a point B here. Okay. Then now you apply your gamma i's to A and B, right? What happens in here when you apply your gamma i's to A and B? These guys get sucked towards the X, right? So gamma I A and gamma I B both get sucked towards X, and gamma I inverse A and gamma I inverse B gets sucked towards Y. Okay? So since your map is rho equivariant, this tells you that if you look at rho of gamma I of CA and rho gamma I of CB, okay, these both get sucked towards C of X. Okay? And rho gamma I inverse of CA and rho gamma I inverse of CB gets sucked towards C of Y. Okay? This is by the continuity and rho equivariance of C. Okay? Okay, but now you can take these open sets, right? You can look at the open sets which I call O, or maybe C of gamma n minus of C of A, C of B. Your map is positive, so this is a positive triple. You can look at the O of this, and you apply rho gamma I or gamma n to here. Okay? So this is an open set in your flag manifold. And when you apply rho gamma n to this, your A and B, rho gamma n A, this becomes, what is this, right? This is the same thing as O of C of gamma n minus, right? This gamma n minus is invariant to rho gamma n, so this doesn't change. Then you get rho gamma n, C of A, rho of gamma n, C of B. Okay, but gamma n and A and gamma n B are both converging towards the same point Cx. Okay, so this entire open set is getting crushed down to a point. Okay, similarly, if you take the inverse, rho gamma n inverse of this open set, now you take O of C gamma n plus of C of A, C of B. This open set is getting crushed towards C of Y. Okay? And then by the lemma from last time, we saw that as long as you can find this property, as long as you can find open sets, so that rho gamma n applied to the open sets goes to C of X, and rho gamma n inverse applied to the open set goes to C of Y. This tells you that if you take any F that's transverse to C of Y, and you apply rho gamma n to it, you get sucked to C of X. Okay, so this implies that rho gamma n F goes to C of X for F transverse to C of Y. Okay, this was the lemma that we discussed last time. Okay, and this gives you your strongly dynamics preserving property. Okay, so the key thing of positivity you're using here is that pairs of points along the positive curves gives you open sets in the flag manifold. And so as long as you know where the pairs of, as long as you know the dynamics of the pairs of, or the behavior of those pairs of points, right, under the group action, that gives you control on big open sets in the flag manifold under the group action. Okay? Any questions about this? Okay, so maybe let me put one remark. So since you know that a corollary of this proposition, since you know it's K transverse, you know that these representations are all type preserving. Okay, but in fact, using the positivity, you can prove that if alpha in gamma is parabolic, then rho of gamma. So this is if rho is Hitchin, and alpha and gamma is parabolic, then rho alpha is unipotent with one Jordan block. Okay, so the fact that your K transfers for every K only tells you that this rho alpha is weakly unipotent, right? But if you throw in positivity, you can improve that to show that this guy actually, the semi-simple part is just identity, and the unipotent part has a single Jordan block. Okay. Okay, so I will not have time to talk about Anosov representations much. Okay, so I'm going to short circuit this talk a little bit. Okay, so maybe maybe let me just state this as a theorem. Okay, it's not going to make much sense because, okay, but let me state it first. So this is a theorem that was proven by me, Dick Canary, and Andrew Zimmer. Okay, we show that rho, if gamma is a geometrically finite function group, okay, then and then rho is rho from gamma to PSL dr is K Anosov if and only if rho is K transverse. Okay, so this theorem doesn't make sense because I did not tell you what K Anosov means, but I cannot do that because I have other things I want to say in the interest of time. Maybe if I have time at the end, I'll say what it is, okay? But I'm not saying what it is, but my point here is that there's this notion of what's a K Anosov representation, okay? Complicated definition. But in the case when gamma is a geometrically finite function group, this is the same thing as saying that rho is K transverse, okay? So in particular, right, this tells me that the Hitchin representations are all K Anosov for all K. Okay, so the corollary. Okay, so why is this better? Okay, so there are a few things that I can prove about K Anosov representations that are not true for K transverse representations. So these are things that I really need the geometric finiteness for this to be true. Okay, so here's another, maybe as a proposition. Okay, so if rho from gamma to PSL dr is K Anosov, okay, then if you look at alpha K evaluated on the Cartan projections of rho gamma, okay, then for all gamma and gamma. Okay, so what is this? Remember, this Cartan projection is the logarithm of the singular values, right? And so alpha K is just the difference between the log of the K singular value and the log of the K plus 1 singular value. Okay, and what you can say is that there exists some uniform constants, little big c and little c, so that this is at most c times the amount you translate the base point. And at least 1 over c times the amount you translate the base point. Okay? So remember, for a general function group, when rho is K transverse, right? What we saw last time is that this alpha K kappa rho gamma is going to infinity for any sequence of group elements that goes to infinity. But when you assume gamma is geometrically finite, you can get something stronger than that. You can get linear growth of this guy respect to how much it translates a base point in H2. Okay? So in particular, this tells you, this gives you some consequences. So this tells you that if you are K Anosov, then you have some constant B, right, such that the translation, the length of the group element is roughly alpha K, is by Lipschitz to alpha K of the Jordan projections. Okay? So if I don't want to care about translation distance, I want to look at minimal translation distance symmetric space, right? That's related to eigenvalues. So the log of the kth eigenvalue to the k plus 1 eigenvalue, that ratio, is roughly the length of gamma. Okay? Another thing it tells you, another thing this implies, right, is that if you have a K Anosov representation, then the map from the orbit of the base point in H2 to the orbit inside of the symmetric space, that's a quasi-isometric embedding. So that's also a consequence of this. Okay, so in the case when gamma is geometrically finite, you can say more about the geometric properties of this gamma action. Okay, that's what this proposition is trying to say. Any questions? Okay, another important thing that you can say in the case when gamma is geometrically finite is the stability. Okay, so this is another theorem. Okay, so if gamma is geometrically finite, okay, let gamma be geometrically finite, and rho from gamma to PSL dr a K Anosov representation. Did I say cast? What did I call it? K Anosov? Yeah, I just say K Anosov, right? So maybe I should say cast K Anosov to distinguish that from just regular K Anosov representations that people are familiar with, if people are familiar with it. So the cast meaning that, so Anosov representations were defined by Labrie in the setting where gamma is a co-compact lattice. Okay, but you can generalize that easily to convex co-compact subgroups. But for geometrically finite subgroups, there's this definition that I didn't tell you yet, which is of this cast K Anosov representation, which generalizes that. Okay, so I'm focusing on basically on all of these results are known in the convex co-compact setting already. So the new thing is really when you have cast, what's happening. Okay, so the theorem is that let this be K cast K Anosov. Okay, then the set of cast K Anosov representations inside of the space of maybe I called it, I'll write this as Hom, Rel, no. This is open. Okay, and what is this Hom, Rel, Rho naught? Right, this is the set of rho in Hom, gamma, PSL dr. Okay, so that the conjugacy class of rho of gamma is equals to the conjugacy class of rho naught gamma for all peripheral gamma. Okay, so in the case when gamma is geometrically finite, the peripheral elements are the loops that go around the cast and the flares. Okay, so if I have a cast Hitchin representation, okay, so I require that I'm looking at the space of homomorphisms, the representations from gamma to PSL dr, where you do not change the conjugacy class of the ends. Okay, so in here, this set of cast K Anosov representations is open. Okay, and the proof of this theorem really uses the description of a Anosov representation that I did not give to you. Okay, this flow definition. Okay, so as a consequence of this, you see that the set of Hitchin, if gamma is geometrically finite, function, and then the set of cast Hitchin representations inside of Hom, Rel of, let's say, I take a iota composed with a discrete faithful representation from gamma to PSL2R. Okay, this is open. Okay, so let me say what's happening here. So I take J, a discrete faithful representation from gamma to PSL2R. I post-compose with iota. Okay, so now it's a representation from gamma to PSL dr. So this is an example of Hitchin representation. I look at all the Hitchin representations whose ends, whose peripheral elements are conjugate to this one. Okay, so that is not okay. That is an open. So then you look at the set of Cauchy-Hitchin representations in there. That's an open condition. So why is that, right? Because if you start with any Cauchy-Hitchin representation, I know that it is. If I start with any Hitchin representation of a geometrically finite group, I call that a Cauchy-Hitchin representation. Okay, I know by this theorem that not this one, the previous theorem, that this is a Anosov representation. And by this theorem, the stability tells me that if I perturb that a little bit, right, those remain Anosov, meaning that you have row equivariant transverse maps with some additional property. Okay, and then you can prove that this map actually is going to be positive. Okay, basically using properties of positivity. Basically, the point is that if you have a k-tuple of positive flags, if you deform it so that you lose the positivity, you have to lose the transality at the same time. Okay, and so if I'm deforming, I'm going from my original transverse curve to my new transverse curve, preserving transversality the whole time, the positivity also needs to be preserved. Okay, so you get openness of these Cauchy-Hitchin representations. Okay, and then finally, you have closeness. Okay, so this is not a theorem in our paper. So let me write this as a folklore theorem, because I think experts know how to do this, but I don't think it's written down in the literature. Okay. Which is that these Cauchy-Hitchin representations are also closed. So Cauchy-Hitchin representations inside of this Hom iota J is closed as well. Okay, so basically what's going on? So there's this relatively new technique, right, where people can use the color lemma to prove this kind of closeness so okay, this was started in the case of theta positive representations to POPQ. Okay, Beira-Pozzetti, they prove that those theta positive representations satisfy a color lemma, and they use the color lemma to prove the closeness of these positive representations. The point is that, what does the color lemma tell you, right? Suppose I have a sequence of Hitchin representations that converge to a limiting representation. Okay? The color lemma tells you that no non-peripheral curve, its length can go to 0. Because if the length of some non-peripheral curve goes to 0, the length of the transversal has to go to infinity. But you have a limiting representation, so the length of the transversal cannot blow up. So this means that if you have a sequence of positive representation, the limiting representation needs to have the property that all the non-peripheral curves have eigenvalue gaps. Once you have that, you have attracting and repelling flags. That's a dense subset of your limit set, and you know where those converge to. And you show that that set is positive, which allows you to extend. Okay, so there's an argument like that you can apply to this setting. Okay, and you can prove closeness that way. Okay. Okay, so maybe that. Okay, so I have a few more minutes. So that finishes the story of. Yeah. Yes. Not always. Not always, but okay. So let me write down this theorem. Thank you for bringing that out. So here's a theorem. Okay, so this is proven by Kieson Lee and myself. Okay, we showed. Let me see what's the assumptions. Okay, so gamma is a Fuchsian lattice. Suppose gamma is a Fuchsian lattice. That is not uniform. Okay, I need to have at least one cusp. Okay. Then, okay, and rho naught from gamma to G be cusp Hitchin. G is PSL and NR, PSL DR. Okay, then rho in Hom rel rho naught right, is cast Anosov. Is be K cast Anosov for all K. If and only if rho is Hitchin. Okay, so this is telling you that in the situation where you have a single, at least one cusp, right, then your Hitchin representations must take that cusp, the peripheral element corresponding to the cusp, to a unipotent element with one Jordan block. Okay, so I'm in that situation. I'm looking at that relative the space of relative homomorphisms. Okay, in there being cast Anosov for all K cast Anosov for all K is the same thing as being Hitchin. So this is not true for closed surfaces, okay? Theory bubble has examples, right? The first, these are basically if you take SL2R, you put it reducibly into SL3R, right? And then you put a Fuchsian representation SL2R to get a representation SL3R. Those guys are all K Anosov for all K, but they are not Hitchin. But the thing is, if you do that for a Fuchsian group that has a cusp, right? The resulting element is not going to have one Jordan block. Okay, so if you have this assumption that you have one Jordan block, that gives you enough positivity to force the entire curve to be, enough positivity along your limit set to force the entire curve to be positive. Okay. Okay, so I have 3 minutes left. This actually brings me to the end of my first lecture. Okay, so but you know, my title has entropy, right? So let me at least tell you what's the entropy of a Hitchin representation. Okay, so definition. Okay, let rho from gamma to PSLDR be K Anosov for all K. Okay, now I'm going to let phi be a linear functional in A plus dual. Remember, A plus was my positive vowel chamber. Okay, so what is this? This means that phi is a linear map from my Cartan subspace to R that is positive on the interior of A plus. Okay. Okay, then the phi entropy of rho, okay, is the following quantity. Okay, I'm going to denote it by H phi rho. Okay, so what you do is you count the number of conjugacy classes in your group, right? So that phi, this linear functional phi, evaluated on the Jordan projection of rho gamma is less than t. Right, so your eigenvalues are invariant under conjugation, right? So you want to count the number of conjugacy classes in your group, where a certain linear combination of eigenvalues is less than t. You think of this as some kind of length, okay? And you want to look at the exponential growth rate of the size of this set. So you take the logarithm of the size of this set, divide by t, and take the limit as t goes to infinity. Okay? So if your representation is K Anosov for all K, and you take phi to be as described, then this number turns out to be this limit always exists, and this is a positive number. Okay? Okay, so this guy, in this generality, this guy lies in 0 infinity. Okay? Five more minutes. Okay, so theorem. Okay, let me write down a simplified version of the theorem, a slightly weaker version. Okay, so let gamma be geometrically finite function. Okay, and rho from gamma to PSL dr be Hitchin. Okay, then for any k from 1 to d minus 1, okay, the alpha k topological entropy of rho is at most 1, and equality holds if and only if. Any guesses? Gamma is a lattice. Okay, so this theorem was proven in the case when gamma is a co-compact, is a uniform lattice. This was due to San Marino, right? He showed that as long as you have a uniform lattice and your Hitchin representation, the simple root entropy is 1. Okay, and so what we prove here is that it's at most 1, and equality holds even only if gamma is a lattice. So what's the reason? How do you prove this, right? So the trick is you first show that this entropy here is equal to something called the critical exponent of a certain Poincare series, and you show that that is equal to the Hausdorff dimension of the limit set. But for Hitchin representations, as I said before, Hausdorff dimension of the limit set is at most 1. Okay, but you have to work harder to get this if and only if condition. Okay, you need to do some doubling construction and some entropy drop results to do that. Okay, but I'm out of time, so let me stop here. Thank you.
Questions?
I mean, how do you define the critical exponent? And,
right, so
I mean, basically, there are these two, competing things, right?
Right, so maybe let me write that, okay, here. So now your critical exponent, your critical exponent in the classical situation, you're taking a ball around a base point, and you count the number of orbit points in there of distance less than r, and then you see the exponential growth rate of that side. In this situation, like I said last time, right, the replacement of that is this thing called phi of kappa gamma. Because the kappa gamma is translation distance in the symmetric space, but in a vowel chamber valued sense, and you want to make it a number, you use phi, okay? So what you do, you say you look at
Francois Kant's notion of critical exponent that you're using, I mean, in terms of a function on the Weyl chamber, which is...
Exactly, that one, right? So maybe,
Thanks.
Let me just say that, okay, you pick a phi, you take the same phi as you have, and then you look at the Poincare series, this Q phi rho of S. So this is defined to be the sum over all the elements in your group of e to the minus S. So instead of writing distance of how far you translate the base point, you put phi of kappa of rho of gamma here. Okay? And then the critical exponent of this Poincare series is what I mean. And that turns out, so in the case when, so it turns out that the critical exponent, in this generator, I'm going to denote it by delta phi rho. Okay, so what you show in this case is that h phi rho equals to delta phi rho. Okay, and you show that this is equal to the Hausdorff dimension of ck of lambda gamma inside of the flag manifold. These are the Grassmannians, I guess. Okay, but if I know that my limit map in the entire flag manifold is already Hausdorff dimension at most 1, by projecting the Grassmannians, that's still preserved. Okay.
Well, and what about the usual
in the symmetric space? Yeah, so you can say something about that as well, but you don't have this. So you definitely, from this you can deduce an upper bound. I can't remember what it is, some square root of something. There's some upper bound that only depends. Okay, I should mention that this theorem here, there's a more general version where you allow for any phi. So for any phi that you choose, there's an upper bound, and we can say exactly when the equality is attained. So gamma is a lattice plus some other conditions for arbitrary phi. Okay, but in the case of alpha k, this is the only condition. Okay, and so for the translation in the distance in the symmetric space, again you have an upper bound like this, but I don't think we have a characterization of when when the equality happens. Yeah, so that's another long story. So there's a Patterson-Sullivan theory for cusp Anosov representations in general. Okay. Okay, maybe let me say it this way. So this notion of cusp Anosov representations, I do it for geometrically finite Fuchsian groups, right? But today this has been developed for, you can do it for any relative Anosov subgroup. You can make sense of what is a relative Anosov representation. Okay. So what you can do is for the transverse groups, right? For the transverse groups, so even without geometric finiteness, you can develop a Patterson-Sullivan theory for that class of groups. Okay, and there you have the Hopf-Suji-Sullivan dichotomy, which tells you, if you have a critical exponent of certain Poincare series, if it's divergent type, then whatever, some stuff is ergodic, mixing, whatever, and then if it's convergent type, then it's the opposite. You have the same kind of theorem in that setting as well. But that's a whole other story. Yeah.
Which admit, say, relative Anosov representations. These are all relatively hyperbolic with cusp, hyperbolic relative to the.
Yes, to the cusp group. Yeah, exactly.
And what's the restriction on the cusp groups? They have to be solvable, nilpotent, in general.
So okay, in general, what is a relative Anosov representation?
Yeah.
It is a representation that, okay, you can make the same transverse definition. Yeah. One way you can define it is a representation from your group into some semi-simple Lie group with some conditions, okay, that admit a row equivariant transverse strongly dynamics preserving map from the limit set, the voltage boundary, if you will, into the flag manifold.
Yes. Yeah. And therefore the cusps necessarily have to be nilpotent, for instance.
Weakly nilpotent.
So weakly,
weakly semi, exactly. The same kind of things happen.
Okay, thanks.
Yeah.
If there are no other questions, let's thank Tengren again.